to do, these 5 topics, I want to first of all talk about condition monitoring. Then I talk about the approach often adopted, which is perhaps I term the classical approach compared to proportional hazards modelling. Then I want to blend in economic considerations to the decision-making process. Then I want to talk about applications for CBM optimization. And my work has been driven by very close collaborations with industry. And so I want to finish off by saying something about what I see as the value of university, industry, and collaborations. And I know you have that yourselves at Delft. Here's the analogy. If you ask the question, what's the risk of someone suffering heart failure? Possibly we would all say perhaps their age is important, and maybe there are some risk factors that are important. For someone like myself, I'm sure age is important, but to the audience, I'm sure age may not be important. So younger people tend not to suffer heart failure, but sometimes they do. So the point is, the risk of suffering heart failure may depend upon their age, but it may not. It may depend on risk factors. And if there are risk factors, we often want to know what they are so that we can take some remedial action to try to reduce the risk of heart failure from these risk factors. Well, that's the same as what we're doing with condition monitoring. So instead of the heart, if we have a gearbox, an engine, a transmission, and we ask ourselves the question, what's the risk of heart failure? Sorry, the risk of engine failure? Well, it may be dependent upon its age. It may be dependent on risk factors. To monitor the health of equipment, people often use oil sampling, measure the parts per million of iron, copper, aluminum, and so on in an oil sample, or they do vibration monitoring. There are many ways in which we can monitor the health of an asset, and we get measurements, and we try to understand what the health is from these measurements. But also, perhaps we should take into account the age also of the asset, not just the risk factors. The way I see condition monitoring often being done is people base it on statistical process control, warning limits and alarm limits. It's a very obvious way of monitoring the health of your asset, monitoring certain signals and comparing them to some standards. Well, for sure, that is simple to understand. But there are certain limitations. For example, which measurements should we really pay attention to? Is it the iron? Is it the chrome? Is it the rate of change of the iron? Is it the rate of change of the chrome? There are many, many possibilities. And what we really want to know is what are the key risk factors associated with equipment failure? Also, what are the optimal limits? In the chart you see here, this type of often used in industry, they have limits set for warning and alarm. And if you set these limits and discover you're prematurely removing equipment, what you may just do is increase the limits to try and get better limits. It would be nice if we could do some calculations and determine what I've called their best limits or optimal limits. In the chart we see on the right-hand side of the screen, there really is no influence of the age of the item in terms of its risk of failing. The age is on the bottom there, but really you just pay attention to the measurements and really pay no attention to the age of the item. We often want to make predictions. We have a noisy bearing. When's it going to fail? Well, we can make some prediction, but you can't really do that with this approach. With somebody working UPHM approach, then yes, you can. We're often concerned with remaining useful life. But this classical approach doesn't enable us to make predictions. A very important point is what's the consequence of failure. The more severe a failure is, maybe the lower the limits would be. They want to do more preventive work. But there's no formal incorporation of the consequence of failure in that chart you see on the right-hand side. So our work on CBM optimization just extends and enhances this control chart technique. It's just a different form of control chart that tries to take into account these limitations that I have highlighted on the left-hand side of the screen. The way to do this is to use the concept of hazard using a proportional hazards model, a PHM, which takes into account the age of the equipment and the condition measurements at the time of inspection. My early work with proportional hazard modelling was funded by the Canadian Department of National Defence. And you can see how long ago this was published, 1982. But at that time, I'd been working with a biostatistician who did a PhD at University of California, Los Angeles. And I learned about the technique being used in the medical field to monitor the health of patients under different drug treatments. And I was able to work with her and use this idea of proportional hazard modelling to monitor the health of these engines on the Boeing 707. So the question is, what's the risk of an engine failing in service? Now, what they used to do is they took samples of oil at regular intervals from the engine and looked at the metal deposits and looked at rate of change. If the rate of change exceeded certain limits, they said the engine is not healthy, we should remove it and send it to Pratt & Whitney in the United States for relifing. So that's what they were doing, but they knew that sometimes the report came back from Pratt & Whitney to say the engine was healthy. So in other words, the engineers had maybe been too pessimistic and took the item out of service when it was still healthy. So the Defence Department wanted to get a better decision-making procedure. So I was very fortunate to get access to data from the department. And there's the data I had. I got data from 50 engines. The design life of the engine was taken out of service after 15,000 flying hours. And given that removal rule, of the 50 engines, 42 of them survived 15,000 flying hours. But 8 of them failed before 15,000 flying hours. And the decision on whether to leave an engine in service or remove it was based on rate of change. That was a measurement they were using. So we got data, a lot of data. And using our proportional hazard model, here's what we concluded. I have 8 engines. Engine number 1, I'm calling it, the first one, is the worst one. It was removed from service when it was 11,770 hours old. The iron was exhibiting 5 parts per million iron, and the chrome was 6 parts per million chrome. And when we combine these 3 numbers using a hazard model, we get the risk of failure in the next flying hour as 0.043. But I had similar data for the other 8 engines. Now, what was exciting to us as researchers was look at engine number 8. It was removed from service when it was 7,190 hours old. At the time of removal, the iron was 2 parts per million. The chrome was 2.5 parts per million. And when we combine these 3 numbers, we get an estimate of the risk of the item failing in the next flying hour. And the risk of failure in the next flying hour was really quite small. Now, what you'll notice is I've got an asterisk against the number 8, because after the fact, we were able to get the maintenance reports from Pratt & Whitney to discover what really was the health of the engine number 8. And Pratt & Whitney said engine number 8 could have been safely left on the aircraft. The others that you see with asterisks on them also, Pratt & Whitney said, could have been safely left on the aircraft. So we were very excited about getting these estimates using a proportional hazard model. And what's the proportional hazard model I used? Well, this is the equation we used. The hazard is a function of age and also of the risk factors. And that's a hazard model there. And Z1 is the iron and Z2 is the chrome. So from this very first exploration of PHM for estimating the risk of engine failures, we felt very happy because you'll see that we got 3 of them as having a very low risk of failure, and that was confirmed by the reports from Pratt & Whitney. We didn't get a perfect match, but this was a very good result. So it gave us confidence that this idea of proportional hazard modeling could be value to us in reliability work to estimate the risk of equipment failure. And this is the type of new type of chart that we created. Now, let me just say, for the military, they're often just concerned with risk of failure. But when we talk to industry, they're interested in risk of failure, but they also are concerned with economics. What's the consequence of a failure financially or in terms of outages? So we then took this hazard model and blended into it the mathematics associated with the consequence of failure, and then developed this new type of control chart, which eliminates these limitations I spoke about in the previous slides. So on the x-axis here, you have the age of the item at inspection, and this decision chart comes from a bearing on a pump. It was a particular bearing, and so at the time of inspection, we knew its age. And so every time, and we knew the key risk factors. The most important measurements was a vibration monitoring measurement in the horizontal direction, position 1 of the pump, another vibration monitoring measurement in the vertical direction, in position 1 in the pump, and they're both in the 5th bandwidth. And the weighting to give to these measurements for the horizontal measurement was 20, and 57 is a weighting to give to the other key risk factor. So in other words, from all the measurements in this bearing, we've identified the key risk factors and the weighting to give to them. So when the inspector goes to do an inspection, they get the measurements, use that Z score you can see at the bottom there, the hazard equation, and plot the answer on the red, green, and yellow chart. And this is a chart to minimize total cost. The more severe a failure is, the more red you would see in the chart. And so this takes into account the consequence of failure as well as the risk of failure. And so what this says, to minimize total cost, the best move is to change out the part before it gets into the red zone, or at the intersection of the green and the red. So that was one of the early applications we had of using a proportional hazard model to make good decisions about monitoring the health of a bearing on a pump. So that's where we are early on. Now, we had a lot of interest from industry, and the government of Canada encouraged academics to get support from industry. And if we got support from industry, then the government would match their funding. So I was able to develop a fairly healthy research group, and this is just an acknowledgement to some of the companies who've paid money to the university to fund a research group. And you'll know some of the names here that we had support from France, from ABB, from Xerox United States, a gold mine. So we had funding from many industries who are all concerned with condition monitoring, getting as much life out of their parts as they can before they have to take them out of service or before they fail. So to optimize CBM decisions, using an approach we called EXAKT. I'll say more about EXAKT afterwards, but there are 3 keys. First of all, you have to estimate the risk of an item failing the hazard. Then you need to calculate transition probabilities of going from one state to another state between inspections. And then finally, you have to take into account the economics. The Defence Department was interested in bullet points 1 and 2, not so much in bullet point number 3, but industry is very much concerned with bullet point number 3, the economics. So how do you go from collecting data to building that risk model, a hazard model? Well, you're collecting data, you're collecting lots of data. For all sampling, you've got lots and lots of measurements over time. And from these measurements, you want to calculate the hazard, the risk of the item failing at that moment in time. And to do that, we use a proportional hazard model. Now you can see that previous slide I used, my proportional hazard model only had 2 risk factors, iron and chrome, but you can have others. But usually we find 2, 3, 4 are the most you need. Many are correlated with each other, and so we don't need them all. So we collect data. From the data, we analyze it and figure out the key risk factors. Using a hazard model, we can convert these numbers to the risk of failure at today's inspection. And there's again the hazard model generally. That's the age contribution. Now, many of you may know about Weibull analysis, and that first component is the risk of failing dependent upon age and the type of failures you get. Beta is called the shape parameter in a Weibull distribution. And then you have another part to the equation, which is the contribution of A, of condition monitoring information. And together we get the instantaneous rate of failure. And there's an equation of a hazard model, where the risk factors obviously were lead and silicon. But what's very important here is the constants are estimated from the data. So we have equipment in a different operating environment, where you have to get your own equation for your own equipment in its operating environment. I know many people in the industry, we want to get a site-specific answer. So this is exactly that. It's dependent very much on the operating environment of the equipment, what the risk factor is going to look like. So how does data model hazard? We have to have data. You have to have histories, which tell us information about when the item comes into service and when it comes out of service, and what the measurements are as it progresses over time. And then perhaps you have a failure at some point in time, so you have to have that information as well. So you have to know when the item comes into service, information you get from inspections, and when it comes out of service. It may come out of service because of failure, but it may come out of service because of a preventive removal. And you need to know what type of removal it is. Now, if we just look at that data set there, most of us would spot that both lead and silicon are tracking upwards just before we had a failure. So we might say, well, it seems as if perhaps lead and silicon are the key risk factors. But we don't just look at one history, we look for many histories. And so for my aircraft engines, the Pratt & Whitney engine example, I had 50 histories to examine from start to finish. And so you combine histories combine data from all the histories and get your hazard model that you see there. So once you've got the hazard model, you need to know how these key risk factors, the covariates, change over time. And there's a history we saw earlier. So let me just look at one of these tracks, which is the lead, how the lead moves over time. Look, we'll expand that, and put what I call bands on it, put ranges on it. And by inspection, you can see that if a measurement is in the low band, first band, there's a high probability your next measurement is going to be in the same region. If we look at the data carefully, we'll discover that sometimes it goes from the lowest band to the next level, moderate probability. And if we look at data carefully, we'll discover sometimes it jumps from the lowest towards the highest. Not very often, but there's a probability of that happening. And sometimes when you analyze data, the measurements go down for whatever reason. But you have to look at all these measurements and look at how they transition from one inspection to the next inspection. These are getting transition probabilities. So here's a transition probability matrix for iron. It's a very busy slide, but let me just take my time. If today, for example, your measurement of iron is between 2.5 and 5 parts per million, then between today and 100 days from today, there's a 26.7% chance that it stays the same. There's a 4.9% chance that it goes from the current state to the failed state in 10 days. Around 20 days. So these are transition probabilities we need to get from our data. And if you've got lots of data, you can get these transition probabilities from the data. They're not calculated, it's from your data. So that's what I want to say about transition probabilities. So first of all, you have to get the proportional hazard model, the key risk factors. Then you transition probabilities for all the key risk factors. And then you're going to blend in economics just in a minute. So we saw this earlier, you get your data. From the data, use a hazard model. At each inspection, you calculate the hazard. And you have to decide when you calculate the hazard, what are you going to do? For example, if I tell the inspector when the hazard level is a certain low value, take the item out of service and do a preventive removal. So if the level is set here, that means a lot of the time you'll do preventive work. and very few failures will occur. But if you let the hazard level go higher, then you do less preventive work and suffer more failures. And in the limit, you could not bother measuring and just ignore the hazard. If that happens, all you'll get are failure replacements and no preventive work. And what we need to do is calculate what the costs are associated with different hazard levels, because we want to know the best hazard level to change out the part. So now we're going to ask the question, what about the cost of a prevent removal and the cost of a fail removal? And once we know what these costs are, we can get this cost plot that you see in the bottom of the screen. So for example, if the hazard level is low, you'll do a lot of preventive work, get very few failures, and we can calculate the cost of that. If we let the hazard level go higher, then we'll do less preventive work, but suffer more failures, and we get the cost of that. And if we ignore hazard, then we'll do no preventive work, and we'll just suffer failures. And the cost of that will be simply the cost of replacing the item only at failure. So now we can get the cost plot, we can look at the cost plot and look for the minimum cost. And then say, that's the optimal hazard. At that hazard level, you're guaranteed to be at the minimum of the cost function. And in that red, green, and yellow chart I showed you before, the minimum of the cost function is the intersection between the red and the green. There's the optimal hazard. So you now tell the inspector to go ahead and do the inspections, use the hazard model, and once you get to that hazard level, that's the best time to plan to change out the part, because at that time you're at the minimum of the cost function. And there's a decision chart, and there's the measurements. And once it's into the red zone, you're saying to yourself, we should plan to change it out because we're past the minimum of the cost function. Any dot in the green zone is coming down the cost function. Any dot in the red function, you've gone past the minimum and you're climbing up. This is not to say the part is going to fail, because this is an economic decision, not just a fail decision, but balancing the cost of preventive work and the cost of failure work. The best plan is to change out when these colours intersect. Now, to do this work, we were supported by companies, as you know. Companies don't want mathematics. They simply want a piece of software that is easy to use, but they want to trust that the mathematics behind the software is well checked out. And so we had to decide, well, what are we going to do to call this software? And we had a meeting with ourselves and the consortium members, and a decision we made, we'll call it EXAKT. So that's how the name came about after the first 3 years of operation. So I hope I've given you a flavour of what proportional hazard modelling is all about and how we take measurements, we identify the most important measurements, we build a hazard model, then we get economic consideration taken into account, and we can get the cost function. So let me now just give you 3 examples. The first one deals with that bearing we saw in the pump. It comes from a pulp mill, Irving Pulp and Paper. It's one of the consortium members who supported us. They were taking vibration monitoring measurements at regular intervals, 56 measurements taken regularly. Of these 56 measurements, we were able to identify there were only 2 of them were highly correlated with failure of that bearing you see highlighted on the diagram. Others may have been correlated, but they were correlated with each other. So there were only 2 that were highly significant. 2 key risk factors. Now, the consequence of failure of this bearing was 3.1 times more expensive than changing it out preventively. So that's the economics. And we built a red, green, yellow chart. But the question is, how good is that chart? And it's a bit like what I see being done with machine learning. You have data sets, and you use one for testing, and you use one for building the model. In a sense, that's what we did as well. We looked at situations where there had been a failure and asked ourselves the question, had they had this tool, would they have prevented the failure? And we got a very good result here that had we used our approach on another set of data, we've got savings that were quite important to the company. It was a successful collaboration. These are transition probabilities. It was vibration monitoring. And if you speak to vibration monitoring people, they have charts that tell you what you mean by very smooth, what you mean by smooth, what you mean by very rough, what you mean by failure. So they have these charts. And so we used one of these charts from the vibration monitoring people, and we're able to get these transition probabilities of going from one state to another state between an interval of 30 days. And if you ask, well, what has happened in that company? Well, they hired someone to develop a linkage between the condition monitoring database they had and the EXAKT software. And they now installed the software for everyday use. And as I said, developed a tool to link the relevant databases. The relevant databases usually are the condition monitoring databases and I'll call them the event databases. Information about when an item goes into service, when it comes out of service, why it comes out of service, and if there's any work done between installation and removal. So that was a very nice collaboration we had with that company. And as you can see, there were no pump fails in 22 months and counting, whereas there had 15 fails in previous 5 years for 12 pumps at that pulp and paper mill in New Brunswick, Canada. So that was an example dealing with vibration monitoring. This is just another example dealing with oil sampling, a very common procedure used in industry to monitor the health of equipment. And what they often have are rules like this. If the aluminum is less than 20 parts per million, everything's okay. 20 to 40 is a warning, and above 40 is an alarm. So these are rules that they use. So we had an opportunity to go and look at data from this coal mine. And there's the readings we get today. Aluminum 2 parts per million, chrome 1 part per million, copper 0 parts per million, and so on. So these are today's measurements. And there's the decision chart. And if you look carefully at that, you'll see the key risk factors are iron and sediment. So of all these measurements, the most important ones was that one and that one there. So that's the key risk factors. And that's a hazard model. And taking into account costs, there's the red, green, yellow chart. And you can see that today the answer is don't replace. And we used to meet every 6 months with the companies that were funding us, and we showed them what we were doing, and they'd respond to our work and raise questions. And one of the important questions somebody raised was, well, you tell me today don't replace, but when can I expect to replace? So then we changed the software to enable them to have an output that told them when might expect to get into the red zone. So in this example, the recommendation is don't replace, but they expect to replace 1,271 hours from today. So our work was done very closely with industry, meeting every 6 months, a round table. And one of our consortium members came from Hong Kong, mass transit, and he flew every 6 months to Toronto and participated in our meetings. And this is the result from that coal mine, with 50 wheel motors to analyze. 12 measurements were being taken. The key risk factors were iron and sediment. An estimated cost savings of 22% compared to present practices. In their case, the cost ratio is 3 to 1. The reason it was 3 to 1 is if failure replacement caused some consequential damage. And that's why the cost of changing out under failed conditions was more expensive than changing out under preventive conditions. Now, these first two examples just said the bearing is going to fail, or the engine is going to fail on the aircraft. In our work with the Minister of Defence in the UK, we were able to extend the model to deal with many failure modes of a complex system. The complex system we're dealing with were diesel engines on their frigates. And Tim Jeffries, their reliability engineer from the Department of Defence UK, would come across to Toronto every 6 months and participate in meetings and raise questions and give us examples. We had great collaboration with all these consortium members. They motivated very much what we were doing. And so Tim Jeffries told us they've got a problem with their diesel engine on frigates. Because when a diesel engine fails or is not acceptable to be on board a ship, they bring it into port to change out the diesel engine. And when they're changing it out, they often want to do some other opportunistic preventive work. And they're wondering what other work should we do at the same time. So that was the motivation for us looking at different failure modes of diesel engine. And there's the 10 causes of a diesel engine having to come out of service. And what Tim Jeffries told us is that the first 5 were unrelated to oil readings. We couldn't predict any of these failures from oil sampling. And they were concerned with a condition monitoring approach or sampling. But they said the other ones possibly could detect upcoming failure from measurements of oil sampling. And you can read them just as well as I can, cylinder liners and rings, and so on. So we're now able to make simultaneous decisions for each failure mode of a repairable system. And you can see it red, green, yellow charts. And the yellow just simply means the best decision may be between 2 inspections. That's the yellow is the interval between inspections. No need to spend too much time on this, but you can see we can get different red, green, and yellow charts for different failure modes of a repairable system. So if you're down for one reason, and you think I should do something else, you might ask your question, whereabout is this other failure mode in terms of the red, green, and yellow chart? If it's a long way away, you might say, we're not going to do anything about it. We'll leave it alone until when it comes back into port. But just gives them more information to base their decisions. Now, remaining useful life is an important measurement people are often concerned about. And so what we're able to do is can get a conditional density function, which also gives us the remaining useful life. So there's the density function. Today, the diesel engine is 9,000 hours old, and we know the measurements today from oil sampling. And there's the time to failure of this diesel engine. The mean time to failure can be thought of as the remaining useful life. So the remaining useful life from today is 12,000 hours from today. But what you see, there's a peak a long way before you get to the measurement of the remaining useful life. And it's very valuable, perhaps, for engineers to know that, rather than just base their decision only on the remaining useful life. So we're able to get the complete distribution of time to failure, including remaining useful life. And of course, we get standard deviation. So let me just summarize what this condition-based maintenance optimization is all about using my form of PHM. What you have to have is data. When you saw with my aircraft engine example, our data was data coming from 50 engines. We also had the condition monitoring data between the engine being installed on the aircraft and it being removed. And we knew if it was removed for failure causes or it was removed preventively because it reached its design life. So that data has to come to you from the partner, from the consortium member in our case. From that, we can suck it into our software engine, which we called EXAKT. And coming out of that, we get the hazard model and the transition probabilities. And I call that perhaps an intermediate result. That might be all you're interested in. What are the important measurements? And what's the risk of failure between today and sometime in the future? You can get that from the hazard model and also from the transition model. But you may want to determine the remaining useful life. And you can also get that by using just the hazard model and the transition probabilities. We can get that conditional probability distribution, and the mean time to failure of it is the remaining, what we call the remaining useful life. But in industry, they're often concerned with economics. So if you want to get the best decision to minimize total cost, or to maximize availability, then we have to input into the software the cost information, such as cost of a prevent removal, cost of a fair removal, availability, the time to do a prevent removal, time to do a fair removal. And you enter that in, and then you get a red, green, and yellow chart on which you can get a dot. But we don't say base the decision on that chart. Use some engineering judgment, because you as the engineer may know something more than we have in the software. It may say change out today, but you know you have a change out coming in a few days' time. So you're going to discard the software recommendation and you're going to overrule it. So you then use engineering judgment to actually make a decision. So we want to stress it's not the software that's making a decision for you. We hope it's helping you make a good evidence-based decision. Now, in the last few minutes, I want to talk about some CBM optimization studies. I've already talked about two of them already. One, aircraft engines, bearings on the pump, and fuel motors in the mining industry. But over the years, we've had good collaboration with many organizations in Canada, in the US, in Hong Kong. There's a mass transit Hong Kong vehicle there, and they did the work themselves. Their engineers in Hong Kong did the work, but they used our software, our models. So we had great collaborations with industries in many places and for many equipments. And as I mentioned, a lot of it has been done in collaboration with what I call consortium members, industry. So for the past 29 years, research at the University of Toronto's Centre for Maintenance Optimization and Reliability Engineering has been driven by close interactions with industry, in particular with Seymour Consortium members who fund the centre, and with researchers at universities worldwide. We've collaborated with many researchers. Some have come to us from Holland, from Eindhoven, from Sweden, from many countries. Research students come and spend 6 months or 12 months with us, then go back to their home universities. So we've worked with many researchers at other universities other than the University of Toronto. And this is something I thought I'd just try and summarize. Collaboration with industry, in its broadest sense, often provides fertile ground for the development of new and challenging research ideas. Everyone stands to benefit: students, academics, and industry partners alike. And this is a quote from my project director who's with me for more than 20 years, Dragan Banjevic. And I spoke to him about university industry collaborations, and this is what he said. I think it's very important, so I want to spend time just reading it out with you. He said, "There's no better place for good ideas, for theoretical research, than trying to solve real-world problems posed by the daily life of engineers. Most of the time, the problem does not fit available models, or the data does not follow typical assumptions. You try hard to solve the problem. You find a way, then you get excited. Then you generalize a problem, and this leads to new theories and plenty of research." Now, Dr. Banjevic was a really theoretical mathematician, statistician, before he did some collaborations, but with myself, he really got involved with collaborating with industry, and he's been an outstanding collaborator for many years. So I say this is a previous quote from my colleague, Dr. Dragan Banjevic. He's a statistician, mathematician, with a PhD in theory of reliability from the University of Belgrade, regarding his 23 years as project director at the University of Toronto Centre for Maintenance Optimization and Reliability Engineering. And during these 23 years, Dr. Banjevic guided the research of research students, postdoctoral fellows, and visiting researchers, colleagues with 35 companies from Canada, USA, UK, France, and I can't read the last one from here. I took a copy of it, and let me see what the last one is. Maybe you can read it. I printed the slides out so I could read them. Hong Kong, the last one's Hong Kong. Yeah, we had a great collaboration with Hong Kong Mass Transit, and every 6 months their operations engineer came to our meetings in Toronto. There's some additional references. Elizabeth Thompson, she was my assistant And she wrote an article for the Operational Research Society in the UK titled Improving Physical Asset Management Decisions. It was published in their magazine called Impact to talk about the benefits of using analytics. They were wanting articles dealing with analytics. And it's an easy to read article, and it talked about some of these examples I spoke to you as well about. Also, as Marcia mentioned, I've had good fortune to publish a few books, and the most recent one was last year, 2022. It's a third edition with a former PhD student of mine, Albert Chung, and the mathematical foundation of what I've been speaking about appears in chapter 3 of the book, because chapter 3 deals with inspection decisions. And before I finish, I should acknowledge who's worked with me. As founding director, I've had the opportunity to collaborate with many outstanding researchers and research students during a period of 20 plus years, especially the senior staff, Dragan Bancevic, Neil Montgomery, Deming Lynn, and Alice Ashkenny, with whom I've co-authored a number of papers. And as you read of some of my publications, you'll probably see some of these names as co-authors with me. And of course, we have often postdocs come with us from other universities, and we hire some ourselves. They've also provided me with superb insights into matters associated with the optimization of evidence-based asset management decisions. That says thank you. There's my name, and there's my email address, and there's a picture of going into the university with students with the university in the background. So I do have, I think, 2 supplementary slides. This just goes into more detail about the companies who supported us, and this just stresses that software tool. Here I'm calling it an analytic toolbox, not EXAKT, because all the tools in the analytic toolbox are in the public domain. They're all developed by funding from the government and from companies, and there's nothing secret about that toolbox. Everything is in the public domain. And I'll stop there and say thank you. I think I've finished with 10 minutes to go. But thank you very much. Happy to take any questions.